Thank you. So the next and last speaker of the morning session is Andrea Di Gioacchino, and he will speak us about the traveling salesman problem and recent development. Thank you very much.
Okay, so let me start by thanking the organizers, Carlo, especially Carlo, for this very interesting conference and for giving me the opportunity to present you this work that we did with Professor Sergio Caracciolo during my PhD. Okay, so I have been one of the Andreas, I guess the last one so far at least. So with this, I go to the next slide. No. It's always okay. No, now I understand. But there is no point. Okay, no problem. So this is the picture that you already saw. Okay, there is Professor Caracciolo in the middle, and you can see I'm very interested in this picture because you can see also a younger version of myself here. So this was my actually my quantum mechanics class taught by Professor Caracciolo in 2013. So almost 10 years ago. And then this was actually my first interaction with the professor. And I have a story to tell and also with something to confess. So when I did the final exam of this course, it was actually the very first in-person interaction. And I remember very clearly this exam because the professor started asking me like a massive amount of questions. I actually had to do twice the written part of the exam. Because, I mean, in Unimi, the exams of Professor Caracciolo are renowned to be extremely difficult. And so I actually had to do it twice myself. And at the end, I had like very good marks. So I went to the oral exam, I was calm. But then the professor started asking me question after question of increasing difficulty. And after a time that looked to me like an hour or so of discussions, he asked me one last final question that was in my, okay. So I understood immediately that in principle, I had the knowledge to think about it, but I was so tired. And this question was by far the most difficult that he asked me. It was something about the hydrogen atom. I don't remember exactly. But the most important thing, it was that the question was a yes-no answer. I mean, yes-no question. And so my brain just shut off and I answered yes. So that was a random guess, Professor. And I actually think that he understood because he looked at me, like remained silent for a second or so. And then he told me, unfortunately, the answer was no. And then he sent me home with actually a very good mark. So that was the story. That was my first interaction with Professor Caracciolo, and which later on been developed into he being my PhD advisor. And we worked on this kind of problems. So given that this talk has very broad range of topics, I will very quickly introduce the idea. Here we have a partition function of a typical statistical physics problem. Maybe you are more used to think about sigma as spins and C as an energy, where inside this function of the spins, we have some random variables that are the noise of our system that specify the instance. In the case of combinatorial optimization problems, typically the sigma variables can be spins. Sometimes they are not. They are not necessarily spins. But in general, C is thought of, I mean, the interpretation of C is the cost. And so inside C, there will still be some random variables, but now this will specify the actual instance of the problem that we want to solve. So find the C with the lowest possible, sorry, the sigma which minimizes the value of C. And this can be done, for instance, sending beta to infinity. Then the partition function actually is basically e to the minus beta, the cost of the optimal solution. And then if we take the logarithm of that, we average over the random variables, we divide by minus beta, and then we can obtain some interesting properties about the solutions, such as the average cost of the solution. Now, the issue is that this very, this is, okay. The issue is that this is difficult for in general because the random variables are correlated. So what we can do is to consider the case of infinite spatial dimensions, where we have a mean field theory and the random variables are independent, and then we can use tricks like those used in Médard Parisi papers that are replica techniques or cavity method, or this kind of things. Oh, sorry, I'm quite confused by the. Okay. Anyway. Yes, but it doesn't work as I. Okay. Anyway, now suppose that you. So these are okay. Now, actually, in real life, we are interested in problems where this correlation are present. For instance, say I want to go from Porto San Giorgio, the city where I was born, to Milan, where I did my PhD with the professor, and then to Trieste, which is behind the window of Zoom. Then this can be stated as a problem in the framework that I was telling you, but all the random variables, which here are the length of the roads, they will be clearly correlated because we live in a almost planar, in this case, world where we do have correlations. So the problem is difficult. The mean field approximation is not good, and with Professor Caracciolo, the idea was to try to solve these problems in one dimension, then try to use the knowledge to go to 2D and see what happens in the middle. Okay. Okay, so now this is just a little technical detail. When I say number of dimensions, I mean that, for instance, in 1D, I think about points thrown on a line, and then I compute the distances between points. But all these problems, all the problems I will tell you about, they can be stated on a graph. And so sometimes I will show you the picture in 1D or 2D, and sometimes I will give you the graph version. In the graph, each point corresponds to a vertex of the graph, and then there are edges, and each edge has a weight which is a function of the distance computed in 1D or in 2D. Okay, so now let's consider the problem. The problem is the traveling salesman problem. It is very famous. It is an archetypal hard problem. It's NP complete for those who are familiar with complexity theory. And the problem is the following. So this is the graph view. So I want to find a path going through all the nodes, which is called a Hamiltonian path, that minimizes the sum of the weights of the edge included in the path. So for instance, in this graph, the red one is the solution, I think. As you can imagine, this problem has a lot of applications. I will just tell you about one, just randomly chosen. It has been used to compute the shortest path through all the pubs of the United Kingdom. This is just a vision of Scotland. And this, I mean, just to show you that this is an hard problem, these researchers did it in the equivalent time of 2050 years of computation on a single core. Most of the time was devoted to show that the solution that they found was actually optimal, which is very hard. Because you can have a solution like heuristically, and then you have to prove that this is good. Okay, so this is the problem I will mostly focus on, but I will consider the bipartite version of this problem. So in the bipartite version, consider again the example of the pubs. Say I want to organize a trip with Professor Caracciolo to visit all the pubs in Scotland, for instance. Now, since we are at his 70th birthday, probably Professor Caracciolo couldn't take the pace and visit one after the other these 50,000 pubs. And so he probably would need to stop in some hotels. And so we may want to do one pub, one hotel, one pub, one hotel, and so on and so forth. This is the bipartite version of the traveling salesman problem. In this case, a solution is specified if I give you two permutations, which are the ordering in which I visit all the pubs and the ordering in which I visit all the hotels. Okay. And another problem that I will need for the following is the bipartite matching problem. Now, you will hear more about this later this afternoon by Carlo. I will just introduce very quickly. You can solve it on the same instance or for the same points that I discussed for the TSP case. In this case, the problem consists in finding a matching of each gray point, in this case, with each orange point. And so in this case, the solution is given by just one permutation. And then, for instance, one may want to minimize the total the length of the link matching the points in two dimensions. Now you could ask me, okay, but why are you focusing on such a contrived formulation where you use this bipartite thing and so on and so forth? Well, actually, there are some cases where this bipartite formulation has been used and can be used to understand something about the problem that is difficult in the original and classical setting. There is this example of this very recent work where the Netherlands computer science researcher found an algorithm able to solve a bipartite TSP in 2 minus epsilon to the n is the number of points, and this epsilon is something finite that he could quantify. And it's actually interesting because the previous state-of-the-art algorithm was introduced by Karp around 60 years ago, and it took 2 to the n, okay? And so this improvement was thought impossible unless new ideas about how to solve this problem were developed. And actually, I don't understand completely this paper, but they use the bipartite matching problem inside to propose solutions. It's super interesting. Okay, so this is more or less what I want to do. I will now give you a couple of equations, the cost of the matching problem and the cost of the traveling salesman problem. Okay, you can see here R and B are the positions of red and blue points respectively. And you see that for the matching problem, I have sigma, which is my permutation. And there is a P that you can think that it's equal to 2, just to fix the ideas. And then for the TSP, I have 2 terms. So from red to blue and then from blue to red. Okay, and I sum over all the points, and I have this permutation that specify my tour or my matching. And the important thing here that the reason why I want to show you the equation is that you can actually, you can do it in your mind, actually show that if you rearrange the indexes, the cost of the optimal TSP at fixed distance is larger or equal to twice the cost of the optimal matching on the same points. Okay, keep in your mind this bound. Okay, so always the same. Okay, what happens in 1D? So now the program, I told you we go 1D and then we try 2D. In 1D, we have been able with Professor Caracciolo to show that, okay, the first row is just to tell you, I'm using a sort of graph view, but now we have a bipartite graph, and so you will see all the gray point on top and all the orange point on bottom. And then we have been able to prove with Professor Caracciolo in this work that the optimal solution has always this shape independently of the actual position that the points are in, and this is the so-called shoelace tour. Okay, it has this shape. This is another possible tour that is bipartite, but it's suboptimal. The one there has always lower cost. And so once we know this, we know the properties of the solution, we can actually take the integral, so take the average over the position of points. We computed it in a very general case, also thanks to this generalization of Selberg integrals that we found. And what we discovered, the surprise is that actually, surprise for me at least, that the cost of the optimal traveling salesman problem is equal to twice the cost of the optimal matching when the number of points goes to infinity. So the bound that I was telling you about is saturated in 1D. Okay, can we say something in 2 dimensions? And this is the main result I want to. So I don't know by heart, but we can check. I mean, we have the equation for all n, thanks to the Selberg integral, in both cases. Okay, at least for p larger than 1. I think for p larger than 1. I have to check. I can check and tell you. In 2D, what happens is that we cannot use the same program, mainly because we cannot characterize the shape of the solution, which was the key step in 1 dimension. We cannot say the solution is this cycle, because this would be basically equivalent to prove that P equals to NP, mostly. I think, at least. But we know several interesting properties. First, we know that the two-dimensional monopartite TSP has this property that the distance between two consecutive points scales as 1/√n. And also we know that in the case of the matching problem in 2D, there is an extra square root of log n in the numerator, and that I think Carlo will explain you the idea of why there is this difference in cost. Here I will just use that result to build a scaling argument to show you what happens in the large n limit. Okay, so consider now my set of points. I have some gray points and some orange points. I want to build an Hamiltonian cycle, so I do as follows. I first solve the matching problem, the bipartite matching problem. This is the solution of the bipartite matching problem. Then I solve the TSP. This is hard to do, but I can do it. I mean, at least in my mind. I solve the monopartite TSP on just one kind of points. And then I use this solution to link together the pairs that I built previously. Okay, so I had a valid, I get a valid Hamiltonian cycle, so a valid path visiting all the points, which is bipartite. That's nice. And of course, by definition, the cost will be higher than the optimal one, higher or equal to the optimal one. Okay, could be the optimal or it's worse. And in turn, the cost of the optimal is at least twice the cost of the optimal matching. But what we did now with Professor Caracciolo, we showed that this cycle that we built, thanks to the scaling properties that we knew, has a cost that goes to twice the cost of the optimal matching in the large n limit. And then, of course, since we have this ordering relation between the costs, among the costs, then also the cost of the optimal one has to go to twice the cost of the optimal matching. And this leads us to a prediction, which is exact for the p = 2 case, where we actually know how to compute the cost of the optimal matching in 2 dimensions, which is the one there. And that has been proved recently and extended actually to the most general possible case by Luigi Ambrosio and collaborators in this very recent work. This is mathematics, so far outside my expertise. And okay, this is what I wanted to tell you. The conclusions, okay, I hope you followed. So I will not say that again. What I want just to add some like open problems looking forward. I kind of promised you at the beginning that we would like to understand what happens in the middle between 2D and in-field, so infinite D. And this is very difficult in general. And at a certain point, we had an idea how to do that. And this involves using this this special flavor of random matrices, which are called Euclidean random matrices, introduced by Mesat Parisi. I mean, we would like to do it. We are trying to do it, but so far our attempts were unfruitful. I can tell you more if you really want to know, but okay, that's it. So I would like to thank you all for your attention, and especially thank Professor Caracciolo for having been the guide during the work that led to these results. And I had here a blackboard. I added here a blackboard to remember all those nice morning, afternoon, and days that we spent in front of a blackboard doing the computation that at the end led to these results. So thank you, and thank you, Professor.
Thank you very much. Questions?
I know that lunchtime, I try to be short. Another strategy for doing TSP in dimension 2, and let me talk especially of p = 2, exponent p = 2, would be that you have your initial configuration bipartite, say that size is even, say size is 1024, I don't know. Then you bipartite randomly the 2 colors, say blue and red. You do blue and cyan and red and orange. And then you construct the optimal transport from blue to red, from blue to orange, and so on, the 4 of them. And then you do the equivalent of these. I don't remember the name that you said.
Scholesing, yes.
And if I'm not mistaken, there must be a way of doing that ensures that you are doing that cyclically. Say that you go from sigma 1, pi 1, and then sigma 2, pi 2, and so on, using this blue, orange, and so on. And the nice fact is that at p equal 2, you can calculate the average energies of these by using the famous formula Caraccio, Lucibello, Sicuro, Parisi, some alphabetic order. And as the cutoff is moving, you have a difference between the bound and the TSP, the heuristic TSP, which is of order 1. And the quantity is the log n. So the ratio is 1 over log n. So this will be
another option.
Yet another prediction of the famous formula. I'm a bit messy, but that's an idea you can think about.
I mean, maybe I will ask you again to start from the beginning, because I kind of got it, but I'm not sure. But yes, I think it's interesting, at least in this P1 case.
Thank you.
Okay.
Other questions?
Where is the question?
If no other question, I see no questions. So thank you again.